Hello and welcome. I'm Sam Califer, your host for Vision, the show where we talk all about the College of Arts and Sciences as well as its faculty and students. Today I'm joined by Dr. Jon Woody, an associate professor in the Department of Mathematics and Statistics. Thanks so much for being here.
Oh, thank you for inviting me.
Yeah, I'm excited to have you on and talk about all the work you do. But first, I was hoping you could just introduce yourself, tell me about your professional experience and how you came to Mississippi State.
Yeah, I came to Mississippi State after obtaining a PhD in mathematical sciences at Clemson University. And so, of course, that meant that I should be a statistician here at Mississippi State. And so my focus actually was statistical and stochastic modeling. And so there was some interesting work going on here at the time. There's a fabulous supercomputing resources here. Mm-hmm. And so I was actually interested in what's called change point detection, and in particular in snow data sets, snow-related time series. And so it just seemed like a good place to come and practice my profession.
Sure, yeah, and we're happy to have you on and have you here at the university. And yeah, the supercomputer is one of the best in America, from what I understand. Mm-hmm. One of the strongest at American institutions, and so I'm glad you could come here and have access to that. And yeah, anytime I get the chance to speak with someone who is a math person, that is always so interesting to me because their mind is so different from mine. So could you tell me a bit about what do you research and what are you trying to discover?
The way that I approach it is I like to see raw data, and then I like to talk with domain experts that have relevant questions of interest in that data set. And then from there, what I try to do is figure out if their questions are answerable, and if not, are there closely related questions that you can answer. And so at that point in time, if you have some already built statistical tools that are available, you go ahead and implement those. Typically, at that step, you're also doing what's called exploratory data analysis. You just like visually look at the data by making various sorts of, histograms, time series plots, whatever. It depends on the data, of course. And you try to get some idea of some summary statistics. And then if the question is answerable with methods, you use those. And if there's not methods that already exist, at that point in time, you'll go ahead and build new statistical models. And so that's an exciting part for most academic statisticians. And after you build those, then you want to quantify the distributional theory for how the statistics, which for a statistician is just a function of the data, how they behave, they behave in terms of the randomness of the data sample that you actually have. So.
Sure. Yeah, so you're helping, in a way, I think you help researchers answer their questions by making the correct kind of models, and you know how to find the answers that they want. Would that be correct to say?
Well, I give them I know how to build the tools to answer their questions. The answers might or might not align with what they believe.
Right.
The data is what the data is. But certainly the goal, if and when it's possible, like to try to get the best possible results that we can quantify statistically.
Sure.
So give a sort of a degree of confidence in your solution, or in the solution that the data presents as well.
Sure. Yeah, and so related to that, I wanted to have you on because you are on a new research project. A group of scientists are studying snow cover and climate patterns in the northern hemisphere. So can you tell me a bit more about that project and what your role is on it?
Sure. So this was a pretty involved project. We had scientists from several institutions, the University of California at Santa Cruz, University of North Carolina at Chapel Hill, two scientists here from Mississippi State, myself and Jamie Dyer, who's playing the role of a climate scientist, and University of Northern Florida, UCGA. And so this work was actually had funding from the National Science Foundation. And so the goal was to study trends in the presence of snow. I can go into detail on that if you prefer.
Sure.
All right, so Basically, what we have are satellite flyovers. They fly over the entire Earth every day, taking pictures. And over the northern hemisphere, you would get basically a photo a day, and you look and make a guess, or not a guess, an assessment of whether or not snow exists at a given location for every location in the northern hemisphere. And so the data set we had was basically what you call a stereographic projection of the northern hemisphere onto a Cartesian grid. So basically a 88 by 88 grid. It's like you're looking down onto the North Pole, and you see basically a bunch of ones and zeros. If there's snow at a particular location, there's one. If there's not, there's zero. Those ones and zeros are determined by meteorologists and have been since the late 1960s. So it was a data record of weekly assessments of the snow cover from that last approximately 62 years at the ending time of the study. And so our goal was to assess whether or not those pixels that were either 0 or 1 were exhibiting any trends. And was the total area increasing, decreasing, or were there any other patterns in the snow cover?
Sure. And I'm sure that's something that people have been trying to study for a while, but I think your expertise in mathematics and statistics aids in this project in a way. So could you talk about that? How does your expertise help figure this kind of stuff out?
Sure. So at the end of the day, we are looking for a trend. And so even, students in high school, middle school, maybe even these days, learn the idea of pitting a trend or fitting a simple regression line to data. All right. Now, if your data behaves well, is continuous, can take on any value in range. Say like rainfall amounts are continuous. It can be pi inches of rain, pi minus 1 inches of rain, 1 inch of rain. Here the problem is we're dealing with binary data, 0, 1, and so if you look at an entire year of data at a particular location, it's just going to be a string of zeros and ones. Making that even more complicated is the fact that the data is correlated. So if you're in the northern hemisphere and there's snow on the ground in the middle of winter, there's likely to be snow on the ground at the very far end of the northern hemisphere, in the Arctic regions, if you will. If there's snow on the ground one week, it's likely to be snow on the ground the next week.
Right.
And so that correlation in the data really wreaks havoc on your trend estimates. And so what people haven't been able to do until we study this data is accommodate those correlations, and so that when we do perform our trend estimation, we can assign some statistical significance to those trend estimates, and we can perform hypothesis testing. Do we believe the snow is going down at a particular location? Is it going up at a particular location? And to what degree can we quantify that? So that's what we did that was new in the study.
Sure.
Or part of what we did that was new in the study.
Yes. Yeah, I think because of your expertise in statistics and math, you know how to ask those questions, and you know how to make the model to get the best answer, I guess. And so it's not just enough to have a climate scientist do this. They need to be paired with a mathematician.
They absolutely, there needs to be collaboration among the sciences, and that is of critical importance in climate science because the processes are so doggone complicated. When you have data, you need to make sure that you're not over or under representing how confident you should be in anything, in any trends or anything else that you have estimated.
Sure.
And and we speak different languages, and so a lot of times that's the fun part, is to learn the language of the climate scientists and for them to learn the language of the statisticians, and that's fairly common. In fact, the name we call those outside experts are domain. Actually, we call them domain experts, and so we have to learn how to communicate with them, and it's ever changing as you switch domains.
Sure.
So if you go to economics, you're going to have a different set of language that you'll use, and so on.
And it's pretty common for a mathematician to work with these domain experts collaboratively, like you are now.
Yes. Yeah, well, it's becoming more and more popular. In fact, the term data science is up for grabs. But I think in a lot of ways, this is my personal opinion, is the field of data science is statistics working with domain experts.
Sure.
And so it's not unlike, in my opinion, statistics is kind of morphing into data science in some degree. It's not unlike the turn of the 20th century when you had physicists who were trying to build mathematical and statistical, early statistical methods. They weren't, it's debatable what you should call those at this point in time, but they were trying to perform experiments, and so they would set up things and actually collect data and make decisions on whether or not they thought this or that physical property existed and maybe why. And so now that everything's gone digital, data scientists and statisticians are doing that same thing, but it's vastly different types of data. So it's still all the same process of science.
Sure.
And so I think here at State, our statistics program offers the fundamental building blocks that you need to better understand, these the more commonly seen and used types of models.
Sure, yeah, and I think that's another reason I wanted to have you on, is because when people think about getting a degree in math or stats, they're thinking they're going to have an office job or they're only doing math and stats. But I think your work is a good example of how it can help solve real world problems. It can be applied to the real world in more tangible ways than an undergraduate might think. And so interesting. We've got just about a minute, but could you tell me a bit about how you hope this research can help mitigate the impacts of extreme weather events?
Well, I hope I hope that we can get the appropriate and correct results to folks who can make the best decisions possible.
Sure.
And so if there's too much snow in a given region late in the spring, and rain is coming, and a statistician can point to the fact something's going on here that's abnormal, and the climate scientists have domain expertise on how that might affect things, then hopefully these types of mergers will help things in the future.
Sure. Yeah, it's important. We all have a role to play to get the closest to the truth of this information that we can get, and then get it to the right people for them to make the right decisions. So interesting to hear. Thank you so much for joining me today. And thank you all for tuning in to this episode of Vision. We'll see you next time.